I want to talk about what to do for higher codimension. And to motivate this, I want to say a little bit about the proof of this result, point out what the main ideas are and where the main problems are when you want to go to higher codimension, and then justify or see really what we need to go to higher codimension. That's mainly algebraically the theory of parabolic subalgebras, and geometrically then horospherical decompositions. Yeah? So the outline of the proof. So when we want to classify homogeneous codimension 1 foliations, so we pick such a foliation f. Yeah, so there is this pointer here. How does that work? So we have a homogeneous codimension 1 foliation f. And any such homogeneous foliation, by definition, is induced by the action of some subgroup of the isometry group of the symmetric space. Yeah, so we have this group H. Well, of course, there can be many groups H. And the first step in the proof is somehow to reduce the group H to some kind of canonical form. Try to simplify it as much as possible. And the idea for this is, actually I draw this on the board here, when we go to the Lie algebra, I always like first to linearize, because that simplifies the situation. So we look at the Lie algebra H, and the standard theory of Lie algebras tells us, this is a beautiful theorem by Levy and Maltsev, that we can decompose H into a sum of a semi-simple subalgebra plus some solvable subalgebra. Every Lie algebra can be decomposed into a sum of a semi-simple one and a solvable one. This is not actually a direct sum of subalgebras. In fact, it's a semi-simple, it's a semi-direct sum. So, I mean, or sometimes one indicates this just by a half circle. Yeah, so it's a semi-direct sum. Then this semi-simple group, now semi-simple Lie algebras are just direct sums of simple algebras. Yeah? So every simple Lie algebra is either compact or non-compact. So we collect all the compact ones, we collect all the non-compact ones. So what we here get, this we can decompose into a compact one plus, and this is in fact now really a direct sum, plus some non-compact one. Okay, this is a decomposition of the semi-simple one. Now I decompose the non-compact one. That's what I talked about yesterday. We have an Iwasawa decomposition. So this one here we can decompose according to Iwasawa into some H. So it's again compact. So maybe I should write now H prime. And this is compact. This is the K part I talked about in the Iwasawa decomposition, plus, and then we have some solvable part. This was the A plus N part. Yeah. So this is standard theory of Lie algebras, which I apply here. So I get this decomposition. So now we see what we get is, here we get some compact Lie algebras, here plus here. And then here we get solvable, solvable plus solvable. We get solvable here. Okay? So I put all the compact bits together and the solvable bits together. Yeah, I get the decomposition into compact plus solvable bits here. Now what happens with the compact part when I when I exponentiate, we get the corresponding compact group. And then there is a beautiful theory, a fixed point theorem by Cartan, which says that when you have a compact group acting on a Hadamard manifold, so on a space simply connected, and non-positive curvature, it always has a fixed point. Yeah? So the corresponding group here has a fixed point. Yeah? So we fix this, we take this point. Since then this bit fixes the point, only this part is left, the solvable part. Yeah? But then what we see is that but the conclusion from all this decomposition is that there must be a solvable subgroup of H which acts then transitively on the orbit. Yeah? Because the compact part fixes the point. Yeah? This is the first step. Yeah, so there exists a connected closed solvable subgroup of H which acts transitively on one orbit. That's what we prove here, on the orbit containing the fixed point of the compact part. But then since it acts transitively on this orbit, it must, because we have a codimension 1 foliation, just because it preserves distances, it must act transitively on each other orbit as well. Yeah? And then, so we have this solvable group, and then one can use somehow, that's a bit more difficult, structure theory of solvable Lie algebras to prove that in fact one can find such a group that acts simply transitively on each orbit. Yeah? So in other words, in the first step we can reduce. So what we do is, we can assume that H is solvable and acts simply transitively on each orbit. Yeah? That's quite a nice reduction. That comes from structure theory of Lie groups. Now in the second step, right, now when we have a solvable subalgebra, a solvable subalgebra always must live in a maximal solvable subalgebra. Maximal solvable subalgebras have been classified. Yeah? And every such maximal solvable subalgebra contains a Cartan subalgebra. Now Cartan subalgebras are nice in the compact case, but not so nice in the non-compact case. They are not unique, unfortunately. Yeah? But every Cartan subalgebra is of this form, T plus A. T is a toroidal part or compact part, A is a vector part. Yeah? And so what one then can take is A. One can take a root space decomposition with respect to A. A is an abelian subspace of P. This induces then, by taking positive roots, a corresponding nilpotent algebra N. And altogether what one gets is somehow this subalgebra T plus A plus N. So this is a Cartan subalgebra. This is a corresponding nilpotent part. And H must live in this one. Yeah, by knowing that H is solvable, lives in a maximal solvable one, this is a maximal solvable one. And then the assumption of codimension 1, and this is a crucial point, and that doesn't work when one wants to go to higher codimension, tells us that in fact A is maximal abelian. So it's maximal abelian, so the whole thing, this subalgebra, must live really in, so we get a suitable Iwasawa decomposition. Everything is compatible. Yeah? So this subalgebra H must lie in this subalgebra T plus A plus N with respect to some suitable Iwasawa decomposition. Yeah, it's somehow what we now found is this solvable subalgebra H, but this lies nicely with respect, in G, with respect to a suitable Iwasawa decomposition. Yeah? So we have our Lie algebra G, and then here we have an A plus N, and there we have G, no, that's not G, that's K, the compact part, and somehow H lies in there. Yeah? So this works nicely in the codimension 1 case, but not in the higher codimension case. Yeah? Finding this Iwasawa decomposition. So the third step is, what one can prove is, Now H, we can project H onto A plus n. Yeah? So if we forget the toroidal part, just forget about this here. Yeah? H lives in here, so just forget this component. We have a natural projection onto A plus n, and one can prove that this is a subalgebra of A plus n. Yeah? So what we get here in the projection is H A plus n. Now this must be a subalgebra of codimension 1 in A plus n, because of the assumption of codimension 1 foliation. Yeah? So now we arrive at the question here, what are the subalgebras of A plus n of codimension 1? And that's a simple problem which can be solved, a simple algebraic problem. Classify the codimension 1 subalgebras of A plus n. And they're all of the form, well, necessarily they must be, they can be obtained by just you pick a vector psi, yeah, and then this spans a one-dimensional subspace. So it's the orthogonal complement of this vector in A plus n. So then the algebraic structure is known, A plus n. I wrote this down. Yeah, n are the root spaces, sum of positive root spaces. A is this abelian subspace. And then using all the algebraic structure one can work out that this vector psi must be either in the maximal abelian subspace, or psi must be in a simple root space, or actually in the, I have to extend it by one dimension, in the corresponding root vector. You see alpha is a one form, and then one has corresponding vectors in A corresponding to the one form. Yeah? So there are not many possibilities really for codimension 1 subalgebras. Yeah? And you see where in our classification where the real projective space comes from, and then the simple roots. This is where the real projective space will come from, and this is where our other foliations will come from. So then, in the fifth step, we investigate the orbit equivalence of the corresponding homogeneity 1 actions. You see, what we have done here is, this is our original foliation is given by the group corresponding to this Lie algebra. What I construct there is a kind of model subalgebras or model foliations. Yeah? But we don't know how they are related to each other. So we have to investigate how are they related to each other. Here we get some foliations, there we get a foliation. How are they related? Yeah? So we've got this subalgebra. So in the first case, when psi is in A, one can show that we get really the same foliation from this group and the group where we project onto A plus n. It's really the same foliation. That's very nice. And the same happens when psi is in the corresponding root space, is in the root space corresponding to the simple root alpha. They induce the same foliation, but it is not true if psi is actually a combination of a vector in the root space and then of the corresponding root vector. But what one can show is that the corresponding foliations are, well, orbit equivalent, or there is an isometry moving them into each other. Yeah, so geometrically we don't get something else. But it's a bit more complicated, the situation. We don't have the same foliations. They're just isometrically congruent. Yeah? In fact, what we get in this case here is we get just the leaf through O, in this case, is just a different leaf of the original foliation. Yeah, that's what happens. And eventually, and this is actually that's the most difficult part and the longest part of the classification, is we have to investigate the orbit equivalence of these model foliations we get. Yeah, so this tells us we actually can restrict to these foliations here, and then we have to investigate what are the isometric congruence classes of these. Yeah? And here, in the first case, so this A has dimension R. This corresponds to the rank of the symmetric space. Yeah? And one can show that So we choose a line in A which corresponds to a point in the corresponding real projective space. Yeah, this gives a codimension 1 foliation. And there the well, basically what we get are incongruent foliations, but if there is a symmetry of the Dinkin diagram, we get something that produces congruent foliations. And in the other case, what we get here, so in the case when Xi is in a root space, one can show that it doesn't really matter how Xi lies in the root space. Each choice of a line in a simple root space gives isometrically congruent foliations. Yeah? So this is different to the case where we choose a line in A. So here the line really doesn't matter. Here it matters where it lies. Yeah? So in the end what comes out is that these foliations are really parametrized only by the root space, but we don't have to take care of the line in the root space. Yeah? So this is where these R points come from. Okay. And the problem with higher codimensions is also when you want to try to find model foliations, you think about, well, we have to find codimension, well, subalgebras of higher codimension. But then classifying even codimension 2 subalgebras, that's already a problem. I mean, we haven't succeeded with this. Yeah? Codimension 1 works nicely, but trying to do this step for higher codimension doesn't work really. So that's another problem when one wants to go to higher codimension. Okay. So to find another way dealing with this is what we need are parabolic subalgebras, and I want to talk about them. So first I explained the algebraic theory and then what it means geometrically, and also again I discussed this for the special case of our model symmetric space given by the special linear group. Okay. So the abstract definition, the abstract algebraic definition for a parabolic subalgebra of a semi-simple Lie algebra is that so subalgebra is called parabolic if it contains a maximal solvable subalgebra. B, I call it B because such subalgebras are often called Borel subalgebras. Yeah? This is it's a simple definition. Subalgebra is parabolic if it contains maximal solvable subalgebra. Doesn't really say anything interesting. You don't really know what to do about it. But they can all be written down explicitly and classified, and this is quite elementary. So remember, by lambda we denote the set of simple roots. Yeah? This is a set consisting of R elements. And now we choose a subset of this. This is a set with R elements. We choose an arbitrary subset. Could be the empty set, a set with 1 element, a set with 2 elements, anything. And from that set, I'm going to construct a parabolic subalgebra and then say that actually all of them are obtained in this way. Yeah? So it's a simple construction for such algebras. So what we do is, by choosing this subset phi of lambda, what we in fact choose is a set of simple roots. Yeah? Lambda is a set of simple roots. We choose a subset. And since this is a subset of simple roots, it will generate a subset of the root system. Yeah? These roots span a vector space, and I just take the intersection with the roots that are given by lambda. Yeah? So this phi generates a subsystem, a root system, in this way, and I denote then by sigma phi plus the corresponding positive roots. And then I take the intersection of all the kernels of these roots. Remember, each root is a 1 form, so the kernel of a root will be a hyperplane in A. Yeah, so what we have here is the intersection of hyperplanes. If the cardinality of phi is k, yeah, then we have the intersection of k hyperplanes. Now this is the kernel here. This gives also an abelian subalgebra. And now what we do is we define a subalgebra of G by taking the normalizer of this abelian subalgebra Ng. Now one can show that this is equal to the centralizer of that A phi. That's the same. It doesn't matter if we take the normalizer or the centralizer in this particular situation. Or if you like, in terms of roots, that's very simple then. We take the zero eigenspace and we add all the root spaces corresponding to the roots which are generated by our subset phi. Yeah? So it's just the zero eigenspace plus all the other subspaces of root spaces corresponding to phi. And this is a reductive subalgebra, L phi. And then what we also have is we take all the positive root spaces which are not generated by phi. Yeah? So I subtract those which are already in here. Yeah? So I just keep the positive root spaces which are not in here. This gives a nilpotent subalgebra. It's a subalgebra of n. Yeah? And then one can show, this is a property of the root space of roots, is that L phi normalizes n phi. So when we take the sum, this is again it's again an algebra, it's a subalgebra, and this is a parabolic subalgebra. This is known as the Chavalla decomposition of the algebra. Yeah? So to summarize, we have this set of simple roots. We choose an arbitrary subset. This determines, in quite a natural way, a reductive algebra, a nilpotent algebra. We take the sum. This gives a parabolic subalgebra. Yeah? But we need to go one step further algebraically. This is not what we need for our investigation. So this abelian subalgebra, which we got from the root system, we now take the orthogonal complement of it in A and denote this by A phi. Yeah? Okay. So we define another subalgebra by, we now remove, we take the orthogonal complement of A phi in the reductive subalgebra L phi. What we then keep is again the reductive, what we get is again a reductive subalgebra. And in fact, this algebra is, again, we take all the root spaces corresponding to our choice of phi. The only difference is actually in G0. Yeah? We're taking something away in G0 when we construct M phi from L phi, namely it's just this bit in A. Yeah? So that's the only change here. It's really a small change. And then when we take the derived subalgebra, so we bracket M with itself, what we get is a semi-simple subalgebra. Or this is actually the same subalgebra that we get when we bracket L with itself. Okay. We denote the center of M phi by Z phi. Yeah, so then M phi is decomposed as Z phi plus G phi. This is the usual thing. Yeah, when you have a reductive subalgebra, M phi is reductive. It's always a sum of some abelian algebra with a semi-simple one. So this is the semi-simple one. This is the abelian one. Yeah, this is just the general theory. And then what we get is, you see, what we now do is L phi is decomposed into M phi plus A phi. So we get M phi plus A phi plus N phi. And this is what is known as the Langlands decomposition of the parabolic subalgebra. Yeah? So that's an algebraic construction. Doesn't say much, but this is exactly what we need. And each parabolic subalgebra of G is conjugate in G to Q phi for some subset phi of lambda. Yeah? So this is the main statement about parabolic subalgebras and their classification. So there is a one-to-one correspondence between parabolic subalgebras and subsets of a set of R elements. So there are 2 to the power R parabolic conjugacy classes of parabolic subalgebras. Yeah? Now what does this mean for, I want to get one step further, maybe not. So what we do is we take for a root lambda, we take the sum of the of the root space corresponding to lambda and minus lambda and intersect it with k, denote this by k lambda, and with p we do a similar thing. What we get is p lambda. Then you see this doesn't really depend on lambda or minus lambda, so p lambda is always p minus lambda, k lambda is always k minus lambda, and when we add up g lambda and g minus lambda, the two root spaces, that's the same as adding up p lambda as k lambda. Yeah, so somehow the root spaces, they lie somehow skew with respect to a Cartan decomposition, and I take the corresponding projections onto the k part, p part in the Cartan decomposition. Yeah? That's what I'm doing here. So when we intersect then the reductive algebra L phi with P, what we get is a subspace P phi, which is obtained by, well, exactly what you expect is we take A, this is the intersection of G naught with P, the zero eigenspace, and then the corresponding intersections with P of the root space is G lambda. Yeah? So that's what we get is P phi, and when we take the intersection with M phi or G phi, that maybe doesn't matter, we get a subspace of this. And these are both Lie triple systems in P. Yeah, and Lie triple systems of P, perhaps you remember, they correspond geometrically to totally geodesic submanifolds. Yeah, this will give us the link to the geometry of the symmetric space and to the horospherical decompositions, this construction. Then, yeah. Right. We also have a stabilizer. So K is the stabilizer of the isometric root of the symmetric group, and when we intersect it with the parabolic subalgebra, we get, well, we denote this by K phi. This is actually the same as when we intersect just with L phi or with M phi. Yeah, it doesn't matter. So all the points which stabilize, all the isometries which stabilize a point lie already in M phi. Okay. And then what we get is a Cartan decomposition of the semi-simple subalgebra G phi. Yeah, this is just obtained by we intersect G phi with the stabilizer. So this is the compact part of the Cartan decomposition, and this is the vector part of the Cartan decomposition, which is obtained here. Okay. And then this subspace A phi is a maximal abelian subspace. So let's work this out for our special case. Then it perhaps becomes a bit more clear what I've done here. So let's do the simplest thing first. Choose as a subset phi the empty set. So what do we get? What is A phi? A phi is the intersection of the kernels of the roots in the subset we've chosen. But if our subset is the empty set, there is no root, so we get the entire A. Yeah? And then what centralizes A? There is nothing. So what we have left, the Lie algebra L will just be A. And then N phi will be the positive root spaces. So what we get in this case as the parabolic subalgebra is A plus N, which we encountered already yesterday. Yeah, it's the A plus N in an Iwasawa decomposition. This is the solvable subalgebra. It's the smallest solvable subalgebra you can get in this way. I mean, this smallest parabolic subalgebra you can get. Yeah, so these are all upper triangular R plus 1 times R plus 1 matrices with trace 0. That's the choice phi equal to 0. The other extreme choice, if we choose phi equal to the entire set, what we get in this case is the entire algebra SLR plus 1. So what's really interesting is if we are not in these two extreme cases, so we have a proper subset. Yeah? So let's denote the cardinality of phi by R phi. So and let's assume that phi is connected in the sense that either we have only one element in it, or if there are two or more elements, then adjacent elements in the root system are in the set. So you remember our Dinkin diagram looks like this. Yeah, so what I want to choose is a subset of just adjacent roots here. For example, this or this or this as a subset. Okay? But not something that's disjoint, like this root and that root over there. So what do we get? So one does this construction, puts all the root spaces together. What one gets is a special linear algebra of the corresponding dimension. Dimension r phi plus 1. Yeah, so if we choose, for example, these two roots, what do they generate? Well, this is the root system corresponding to SL3R. Yes, so you can really read it off from the roots you've chosen here. If you choose them, this gives you an SL4. This gives an SL5. Yeah? Plus, and then there is something left to make up for, that's the abelian part in L phi. This is the Euclidean space or an abelian group of the remaining dimension. Yeah? So A phi, this coincides with algebra. In algebra, this is known as the split component of the reductive algebra. Then M phi is obtained by removing A phi. Here, this is the definition. So M phi is obtained by taking the orthogonal complement of A phi in L phi. This is then this algebra, special linear algebra. And this, in this case, also coincides with G phi. So now assume that phi, we are in the general case, phi consists of several connected components. What do we get? So several connected components. So for example, assume we just remove all this and this. So we are left with this. This gives us an SL3 plus an SL3. Yeah, you can again read it off from the diagram. So what we get is a direct sum of special linear algebras corresponding to the connected components. And then an abelian subalgebra of the remaining dimension. Yeah, so in matrix form, what do we get? So we get in matrix form, this direct sum corresponds to the real vector space of r plus 1 times r plus 1 matrices with non-zero entries only in a certain block diagonal decomposition. Yeah, so for example, if we start with this 1, 2, 3, 4, maybe this here. So this corresponds to SL6. Yeah, so what do we get? And then we choose, like, for example, we remove this one. So what is our block? We have, this gives us an SL3, this gives us an SL3. So we have entries in here, 0 here, and 0 here. Yeah? So this would be the reductive algebra SL. So how do we get N? N phi, we have to take the corresponding positive root spaces. Well, we know these are just given by the upper triangular things. So N phi corresponds, so this is L phi, N phi, I do this in red. So we have entries just here. And altogether, then L phi plus N phi gives us the parabolic algebra. And this is the parabolic algebra. So we have just entries and zeros there. We just need trace equal to 0 to have it on the special linear. Yeah, so altogether, these parabolic subalgebras in the case of the special linear algebra are just, you have a block diagonal decomposition, take a block diagonal decomposition, and then you have entries, non-zero entries, any entries in the block diagonals and in the upper diagonals. What's there? And zeros below. And these are all parabolic subalgebras. Yeah, so Q phi is given by matrices with 0 entries below a certain block diagonal decomposition. Yeah. So what looked a bit complicated in terms of root spaces is it's a general algebraic construction for something that is quite elementary in the case of special linear matrices. Yeah, it just corresponds to these block diagonal decompositions and matrices. So the conclusion is Q phi, every parabolic subalgebra consists of all block diagonal upper triangular matrices where the block decomposition of the matrix corresponds to the decomposition of phi into connected sets. Yeah? So now I come to the geometry. What does this tell us about the geometry? So again, now we choose a subset phi of the set of simple roots. By R phi, we denote the cardinality of phi. We have these subalgebras. So A phi is a Lie algebra. We exponentiate. What we get is an abelian subgroup of G. We have the Lie algebra N phi, the nilpotent Lie algebra N phi. We exponentiate, we get a nilpotent subgroup of G. Yeah, all straightforward. Same with L phi. We have a Lie algebra, we exponentiate, we get a reductive subgroup of G, and one can write this down explicitly as the centralizer of this abelian subalgebra A phi in G. And that's what it is like. So we get corresponding subgroups of the isometry group. And then A phi, that's actually quite nice statement. A phi must be or is contained in the center of this reductive subgroup. L phi normalizes N phi. That's no surprise because we knew this already from the algebra level, and when we look at the corresponding groups, that statement remains true. Yeah, so we can take the product L phi times N phi, and this gives us the parabolic subgroup. Yeah, this is corresponding group. And this is, has Lie algebra Q phi. This is no surprise. What is nice is that one can write this explicitly as the normalizer of Q phi in G. So somehow what the parabolic subgroups are, these are the subgroups of G which are their own normalizer. Usually when you take a subgroup, the normalizer will be bigger. Yeah, and the parabolic subgroups are those which actually coincide with a normalizer. That's an algebraic way of seeing them. So Q phi is the parabolic subgroup of G associated with phi. So let's now go to G. Take some time to get to the geometry really here. So we exponentiate, we get the semi-simple group. G phi is semi-simple. We take the intersection of the stabilizer K with L phi, so this is K phi. This is then a maximal compact subgroup of L phi with Lie algebra K phi. We take the product of K phi with G phi. This gives our reductive group M phi. This is closed and reductive, has the corresponding Lie algebra. Yeah, so these are constructions of the corresponding groups. K phi is also maximal compact subgroup of M phi. And the center of M phi is a compact subgroup of K phi. It's a number of algebraic statements. L phi is actually, it's a direct product of groups. It's a direct group product of M phi and A phi. Yeah, so it really splits L phi. Stop now. Yeah. So what do we also see is that Q phi, the parabolic group, acts transitively on the symmetric space, and K phi is the stabilizer. So this is a general fact that every parabolic group acts transitively on the symmetric space. Yeah, we knew this already for A times N. Yeah, that we got from the Iwasawa decomposition. G is equal to K times A times N, so G over K is A times N. A times N is the parabolic group we get from the empty set by choosing the empty set. Yeah, and there we have transitivity, and the stabilizer K phi is just the identity. Yeah? But if we choose a non-trivial subset phi, we get a larger group q phi, which also must act transitively because it contains a times n. Yeah, acts transitively, and the stabilizer is k phi. Right. So now I try to get to the point with these horospherical decompositions. So we saw earlier that we get a Cartan decomposition of g phi. In this way, when we intersect the compact part, it's just the intersection of g phi with k phi. And then we have this p phi s, this is the vector part, and this is a Lie triple system. Yeah? When we take the bracket of p phi s with itself, what we get is the compact part, since this is a Cartan decomposition. Yeah? This is a general feature of a Cartan decomposition. And the corresponding group g phi, the corresponding connected closed subgroup of g, g phi with Lie algebra, g phi, yeah. Oh yeah. So this is the g phi is the connected closed subgroup with this Lie algebra. Now perhaps you remember from yesterday when we have a Lie triple system, and so to each Lie triple system there is associated a totally geodesic submanifold. How do we get the totally geodesic submanifold? We take the Lie triple system, we bracket it with itself to get a compact part. We take the sum of both, the compact part and what we already had. Take the corresponding group, and then the orbit of that group through the origin gives the totally geodesic submanifold. Now this is the Lie triple system. We do this construction. G phi is the connected group. So the orbit through the origin gives a totally geodesic submanifold. Yeah, so this is a Lie triple system. So the orbit is a connected totally geodesic submanifold of M, for which the tangent space at O is the given Lie triple system. Yeah. So each choice of phi of subsets of roots determines a Lie triple system. And determines a totally geodesic submanifold. So, for example, if phi is the empty set, then this must be a point. Why is this? If this is the empty set, then g phi, p phi s, yeah, this is just, this is nothing. This is just the zero vector. So we get just the identity group. So this is just a point. So otherwise, we really get the Riemannian symmetric space of non-compact type. This is no surprise because, well, yeah, every totally geodesic submanifold of a symmetric space is again symmetric, must be non-compact. What is the rank? The rank of this symmetric space is just, well, we can read it off from here. We already have a Cartan decomposition. We know what the maximal abelian subspace is, and we count dimension, and this is precisely the cardinality of phi. Yeah, so the cardinality of phi gives us the rank of this symmetric space. Yeah, so this symmetric space, to say it again, is the orbit of g phi through O. So it can be written as g phi over the intersection of the stabilizer with g phi, but we can also write it as the orbit of m phi through O, and then it's just m phi over k phi. So this is the first step. We produced one totally geodesic submanifold from the subset phi. Okay? Then the next step is, also this abelian subalgebra A phi is a Lie triple system. It's abelian in P, so that's obviously a Lie triple system. And the corresponding totally geodesic submanifold is a Euclidean space. Yeah, that's more elementary. So when we take them both together, again we get again a Lie triple system, P phi, which we encountered before. So we produce the corresponding totally geodesic submanifold, and this is the orbit of L phi. Yeah, this is the reductive part in the Chavalla decomposition. So when we take the orbit of this through the origin, what we get, well, the stabilizer is k phi. This is precisely the Riemannian product of the Euclidean space coming from A phi and this symmetric space coming from the M phi. yeah, in the Langlands decomposition. Yeah, so maybe to summarize this again, starting from the subset phi, we produce the parabolic subalgebra, which has a Langlands decomposition, m phi plus a phi plus n phi. Now m phi, when we look at the orbit of this through O, gives a totally geodesic submanifold, a symmetric space of non-compact type. The a phi in the Langlands decomposition produces this Euclidean space. Yeah, and they're all sitting totally geodesic in the symmetric space. Okay. And this altogether gives us a horospherical, what is called a horospherical decomposition of M. Yeah, so these are the three components of the Langlands decomposition of the parabolic subgroup. We look at the orbits through O, yeah, M phi, A phi, N phi through O, and then M is diffeomorphic to this product. And this is the horospherical decomposition of a symmetric space associated to the subset phi. Yeah, or in terms of manifolds, this is our symmetric space of non-compact type, this is the Euclidean space, and then this here is just, it's a kind of horocycle, it's a nilpotent group. Yeah. In the simplest case, to draw a picture, the simplest case, the real hyperbolic plane with which I started my lecture, we have only one possible choice there, is phi is the empty set. In this case, we get here a point. This is A, this is N. Yeah, and remember the orbits of A and N. So this is the orbit of A, the orbits of A. We have a geodesic, and then the corresponding parallel lines, and the orbits of N are the horocycles. Yeah, so looks like this. Yeah, and when we put this together, now move this over here, so we add all these circles. This gives us the horospherical decomposition of the real hyperbolic plane. Introduces nice coordinates on a real hyperbolic plane. And this is what this business does with the parabolic subalgebras and the Langlands decomposition. It gives you nice coordinates on the symmetric space. Yeah. So for each choice of phi, you get different coordinates. Okay. So let's see what this gives us for our model symmetric space, SLR plus 1 over SO R plus 1. So when we choose phi, the empty set, then F phi is the Euclidean space of dimension R. The semi-simple symmetric space is just a point. N phi is this maximal horocyclic subgroup. So the horospherical decomposition of M is just this Euclidean space times a horocycle. Yeah, it's very similar to this here. Euclidean space would be this line, and then times a horocycle. Yeah? So that's what we get from this choice, just higher dimensions. Nothing really happens for this choice. I just wrote it down for completeness. That's not interesting at all. So this is, again, that's the interesting case. So suppose phi is a non-trivial subset. So again, what we do is, here is our cardinality of phi, and we decompose this into the cardinalities of the corresponding connected subsets. Yeah? So for example here, if this is our subset phi, cardinality is 4, but that we decompose into 2 plus 2. Yeah? So we have these cardinalities. Then the corresponding symmetric space is, well, this is just a product of symmetric spaces of the same type, but just some lower dimensions. Yeah, so in this case here, what we would get is an SL3R over SO3 times SL3R over SO3, yeah, corresponding to these two blocks. Yeah. This gives us the symmetric space the symmetric space, the first one in the horospherical decomposition. Yeah, so the horospherical decomposition of M consists of this space, then a Euclidean space of the remaining dimension, which is R minus the cardinality of phi, and then some horocycle of a suitable dimension. Yeah, this comes from here. You can count the dimension then from here. Okay. So this is how it looks like for this symmetric space. Okay. So now I want to come to the classification of polar actions and hyperpolar actions. Well, first I have to say what they are. So there is a general definition. So we start off with a connected, complete Riemannian manifold, and we pick a connected closed subgroup of the isometry group and denote this subgroup by H. And we say that the action of this group H on M is polar if there is a connected, complete submanifold S of M such that for any point in M, the intersection of S with the orbit through that point is non-empty, and if for every point P in S, then the tangent space of the TPS, tangent space of this section at P, is contained in the normal space, so which means that the intersection is perpendicular. So the simplest example of a polar action, this is where the name comes from, is the action of SO2 on R2. Now what are the orbits of this? We have a point which is fixed under the SO2 action, and then the rotations about this point. That's what SO2 gives. Yeah? So we get the circles centered at that point. Now, what is a section here, or this S, this manifold S? So we want a submanifold S, which is connected and complete, which intersects each orbit and intersects it perpendicular. It's obvious what it is. It's just you can take any line through the fixed point. Yeah? When you take a line through the fixed point that intersects each orbit and intersects it perpendicularly. Yeah, so this is the model action for a polar action. So such a submanifold S is called a section. That's why I call it S. And one can show, well, a polar action on M is called hyperpolar if there exists a flat section, yeah, intrinsically flat, so it's Euclidean space. In this case, of course, well, it's one-dimensional, it's flat anyway. Yeah. And this is not obvious at all, that every section of a polar action is a totally geodesic submanifold. Yeah, so whenever you have a submanifold which intersects each orbit, intersects them all perpendicularly, it must be totally geodesic. Intuitively, it's perhaps clear that it must be that, but it's not easy to show, really. Yeah. There's a problem, it's quite an interesting problem. Classify all polar or hyperpolar actions on symmetric spaces, and in fact this has been achieved already in the compact case. So if one assumes that M is an irreducible, simply connected symmetric space of compact type, then for example the sphere, that's the simplest example. Dadok classified all polar actions on a sphere. So that was already done more than 20 years ago. And then Podesta, Torbergson, 1999, they classified them all on projective spaces. You can write them down explicitly, but I didn't do this because I'm more interested in the non-compact case. In fact, Kohlroas, in some papers, he classified them all on symmetric spaces of higher rank, the hyperpolar actions. And he also showed then in 2007 that every polar action is hyperpolar, really. But there, in the compact case, somehow the situation is somewhat easier because compact groups are explicitly known. One can use Dinkin's classification. The structure is known. That's why one has a simple access to this problem. It's just a matter of writing down all the groups. But for the non-compact case, it's more complicated because of the non-compactness of the groups which are involved. So I want to talk about the non-compact case. We are in our standard situation. We have a symmetric space of non-compact type. And suppose we have a foliation f on M. We say that this foliation is polar or hyperpolar if this foliation has a section or a flat section. Yeah, this is just comes from this definition of polar actions and hyperpolar actions. Okay. So example now. We consider the Chavalla decomposition of a parabolic subalgebra. So then what we look at is, when we look at the orbits of the nilpotent group, then they form a polar foliation on M, which is hyperpolar precisely if phi is the empty set. Yeah. So it's now difficult to draw a picture. I mean, the only obvious picture again is the real hyperbolic plane. Yeah, in the real hyperbolic plane, what is the picture of N? Yeah. The orbits of N. We get again here the Horace cycle foliation. Yeah, this is the foliation given by N. So the orbits of N. So we get this foliation. And how do we get a section? Well, it's just the geodesic here, which is perpendicular to all these Horace cycles. Yeah? So this is the picture in the real hyperbolic plane, and the same picture holds for any symmetric space of non-compact type. Just everything is of higher dimensions. Yeah? So here we take Horace cycles corresponding to the group n phi, yeah? And then what we get is here a corresponding section. Yeah? So these are examples of polar actions and hyperpolar actions only for the special case. As you see, and this is something that distinguishes already the non-compact from the compact case, because in the compact case what Kohlroas proved is that every polar action is hyperpolar. So whenever you have a section in the compact case, then this section is a Euclidean, is flat. Yeah, it must be a torus. Yeah? But in the non-compact case, that's not true. That already indicates that the situation is more complicated there. So let me give some examples now of hyperpolar foliations. Elementary examples. So first we start with Euclidean space, EM, and we pick a linear subspace, and then we take the foliation given by all the affine subspaces which are parallel to the given one. Yeah, it's obvious that this is is polar hyper. What is a section? It's just the orthogonal complement of V. Yeah, that intersects all the leaves of the foliation. Yeah, if we have a foliation here by parallel subspaces, how do we get a section? You just take a perpendicular subspace to one that intersects everywhere. Yeah, so this is an elementary example. So the next one. Now let's pick a normed real division algebra. So either the real numbers, complex numbers, quaternions, or octonions, and denote this by F. And let's consider the hyperbolic space over the division algebra F. So in the case when we have the octonions, we can choose n only equal to 2. There are no higher dimensional octonionic hyperbolic planes because of the non-associativity. So look at the corresponding Iwasawa decomposition of the Lie algebra of the isometry group. And then n is just the sum of two root spaces. Because this has rank 1, there is just one simple root. This is alpha. And then 2 alpha is also a root, just in the case of complex numbers, quaternions and octonions. In the real case, G2 alpha is trivial, so it's just 0-dimensional. Okay? So this is how the nilpotent part looks like in the Iwasawa decomposition, so it's quite elementary. Now we pick a one-dimensional linear subspace in the simple root space G alpha, and remove it, or take the orthogonal complement of this in n. Yeah, so we take A plus this, the orthogonal complement of this line in n. So this is a subalgebra of A plus n. We encountered this already earlier. Yeah, this is one of the homogeneous foliations of codimension 1 we get on a hyperbolic space. This is precisely the one which has a minimal orbit. Okay? So what we then get is a homogeneous hyperpolar foliation on this hyperbolic space. Yeah, it is, but it's not new to us. It has codimension 1. Yeah? It's nothing new. But I want to construct something new out from these data. Now I take, well, it looks elementary now, but it's useful to do. Now I look at the product. So I take k hyperbolic spaces. So F1 is one of these division algebras. I look at the hyperbolic space of it and so on. Fk is one of these division algebras. Can be a different division algebra. It doesn't have to be the same one, yeah? So we take k hyperbolic spaces here. Take a product with a Euclidean space of some dimension. And then I take just the product foliation. Yeah? So what I then get is homogeneous hyperpolar foliation. Now, of course, we have a higher codimension. Yeah? So what is the codimension? We have codimension 1 here, and so on. So here we get codimension k plus, and then it depends on the codimension of the dimension of the orthogonal complement of V. Yeah? So here we have something of higher codimension. But again, it's not interesting. It's sort of elementary construction. I still have to relate this to symmetric spaces. And I'm building up examples here. Now I pick an arbitrary symmetric space of non-compact type. And look at the Langlands decomposition of a parabolic subalgebra of G. Yeah, this is corresponding to an arbitrary set phi. Just pick any of these parabolic subalgebras. Now assume that phi is an orthogonal set of roots. So for any two roots in phi, the inner product between them is 0. Or in other words, the roots you choose from the simple roots are not connected by a line in the Dynkin diagram. Yeah? So you take the symmetric space, look at the corresponding Dynkin diagram, and select vertices in the Dynkin diagram which are not connected by lines. Yeah? So we choose such a subset. So, for example, let's do this again here for our model symmetric space. Let's take this. Yeah, so what we can choose is, for example, this root, and this root. Yeah? So that would be a suitable choice. So what do we then get? What is the corresponding symmetric space we get in the horospherical decomposition? See, what you get when you choose just one root here, the corresponding symmetric space this generates must be a rank 1 symmetric space. Yeah? This is just one root. So the corresponding symmetric space has rank 1, so it must be a hyperbolic space. So this gives us a hyperbolic space, this gives us a hyperbolic space, this gives us a hyperbolic space. So we get a product of 3 hyperbolic spaces times some Euclidean space of the remaining dimension. Yeah? That's what this gives us, this choice of roots. Product of Euclidean, of hyperbolic spaces, an Euclidean space. And we've seen that this F phi, this is embedded totally geodesically in the symmetric space. Yeah, so this is really, now is no longer an abstract product, but it's really living in the symmetric space. Yeah? It's already embedded there as a totally geodesic submanifold. Yeah, coming from the Langlands decomposition and then these orbits and so on. Yeah, so that's really sitting in there, in the symmetric space. And one can read off the, you see, one can actually decide what kind of hyperbolic space it is from the root system. For example, in this case, we see that we must have the real numbers here, and the multiplicity is 1. So in fact, we have a real hyperbolic plane. Here we have a real hyperbolic plane. Here we have a real hyperbolic plane. Yeah? When do we get a complex or a quaternionic or an octonionic hyperbolic plane? Well, when we need a root where also 2 alpha is a root. This happens only when the root system is of BC type, so you can actually then read it off. So this is actually quite an exceptional case, doesn't happen so often. So generically it's only a real hyperbolic plane that we get. And what is the dimension of the real hyperbolic space? Well, it corresponds to the multiplicity of the root plus 1. Yeah? In our case, in our model symmetric space, the multiplicity is 1. Yeah? And then we have to add 1, so we get a real hyperbolic plane. So one can read everything off from the Dynkin diagram. Yeah? So what we then get, now what we take is, oh yeah, so what we saw on the previous slide is now that we have this homogeneous hyperpolar foliation on F phi. Now I erase this. You see here on these hyperbolic spaces, we have these, I draw this again. We have this foliation. Yeah, this is what we have on the hyperbolic spaces. Then on the Euclidean space, so what we have is a number of copies of these. Times, and then we have a foliation given by parallel affine subspaces. Yeah? This is how the foliation looks like on this space. And now the remaining bit is we take a product with a nilpotent, with this horocyclic group, with a nilpotent group. Yeah? And this gives us a homogeneous hyperpolar foliation on the symmetric space. But the symmetric space is just the product of F phi and this N phi. Yeah? So what we then take is times, and then we have just this one leaf. I don't know how to draw this, so it's just like, here is this N, something we add at the end. So for example, the simplest choice you can think of, you choose the empty set, so then we have none of these foliations, and we choose a 0 as the linear subspace, so we just have then points, so that's again nothing, just a point. The only thing that's remaining is just this N. So that's the simplest case. We get this, yeah, in this horocyclic foliation. Yeah, that's a special case of it. And then the theorem, that's what we proved with Diaz-Ramos and Tamaru last year, when we have a symmetric space of non-compact type, that every homogeneous hyperpolar foliation on M is isometrically congruent to one of these foliations that we construct in this way for some orthogonal set phi of simple roots and some linear subspace V in the Euclidean space. Yeah, so that's all. So this diagrammatically shows what are the possible foliations, hyperpolar foliations on a symmetric space. Yeah. So how does this look like now in our symmetric space? Let's discuss this quickly again. We have this Dinkin diagram, the usual one. What does it mean that we choose an orthogonal subset? See if we label them here 1, 2, 3 and so on. So this is 1, 2, 3, 4, 5, 6, 7. So orthogonal just means that we choose a subset that when you take the difference of the numbers, it's just not plus or minus 1. It's just easy to see. And so with K, we denote the cardinality of phi, and then we get as a horospherical decomposition product, as I said, as I mentioned before. These all generates real hyperbolic planes. So this is, we choose K factors. Yeah. You see what K is somehow. K, the maximal number of K, in this case it would be like 1, 2, 3, 4. So it's roughly half the rank of it. Yeah, so this is what the horospherical decomposition looks like. And n phi, we know this corresponds to the set of all upper block diagonal matrices with certain 2 by 2 and 1 times 1 diagonal blocks. Yeah, and all the diagonal entries are really 1. That's what we need there. So in a particular, let's do a special case here, SL5. I prepared this. So this is our Dinkin diagram, alpha 1, alpha 2, alpha 3, alpha 4. We choose as a subset the two roots at the end, alpha 1 and alpha 4. So the horospherical decomposition consists of 2 copies, 2 real hyperbolic planes, yeah, corresponding to alpha 1 and alpha 4. Alpha 1 and alpha 4, so this gives real hyperbolic planes. The remaining dimension for the Euclidean space is E2, and then we have some n phi, and should show up now. So n phi corresponds, you see, we have this block diagonal decomposition here into, so this is a 2 by 2 block corresponding to the real hyperbolic plane here. This is a 2 by 2 block corresponding to that real hyperbolic plane. There is just one remaining in here. So what we need is here ones in the diagonal. Yeah, this comes from the nilpotent. And then we have zeros here. They are taken away by the real hyperbolic planes. And everything else is just arbitrary real entries. So this gives the n phi in this situation. Yeah, so you see the block diagonal decomposition is 2 plus 1 plus 2. Okay. So going back to the general case, general R, rank R, so we have this horospherical decomposition. So on each real hyperbolic plane we select this foliation. On the Euclidean space we select foliation by parallel affine subspaces. And on n phi we select the foliation with just one leaf. And then we look at the product foliation. So the product foliation is hyperpolar, and every hyperpolar foliation on this symmetric space arises in this way. Okay. Okay, and maybe I finish with some open problems we have here. Questions. Is every hyperpolar foliation of codimension 2 homogeneous? You see, I discussed only homogeneous foliations here. But we somehow have the feeling that if we don't make the assumption of homogeneity, just make the assumption hyperpolar, and the codimension is greater or equal than 2, then it actually must be homogeneous. Yeah? That's one of the problems we're thinking about. Another question is actually find more examples of homogeneous polar foliations. I described one example here. When we take the orbits of the horocyclic group n phi, this gives a polar foliation, which is in general not hyperpolar. But it's not clear to us actually what other homogeneous polar foliations there are. Yeah, I mean the hyperpolar ones we can completely classify, the homogeneous ones, but the polar ones, that's not clear to us. at all. And then, of course, once you got the examples, you want to classify them. Right, I want to stop here. Thank you for your attention.
Thank you very much. Do you have any question or comment?